The elementary and homogeneous symmetric functions have a special relationship in the ring of symmetric functions. Let's look at that. Let's do an example first. So the partition 3, 2 transposed equals 2, 2, 1. There's 3, 2, and then if we, this transposed equals 2, 2, 1. Now recall by the Jacobi-Trudi and dual Jacobi-Trudi identities, that we have the Schur function S32 is equal to the determinant of the matrix that has H3 and H2 on the diagonal, H4 and H1 off the diagonal. So that's by the Jacobi-Trudi identity. The dual Jacobi-Trudi identity says we can take the transpose of 3, 2 and put elementary symmetric functions on the diagonal. So we put E2, E2, and E1, determinant of course, and then we let indices increase by 1 every time we go to the right, or decrease by 1 when we go to the left. And S221 is the determinant of the 3 by 3 matrix where we have H2, H2, and H1 on the diagonal. Or we can take the transpose with just 3, 2 and put E3 and E2 on the diagonal. So we can see from this example that it looks like if we replace every EK by an HK, the effect that that map has on the Schur functions is to map S lambda to S lambda transpose. So let's define a map omega from the symmetric functions to the symmetric functions by EK gets mapped to HK. Now this is a well-defined map because the elementary symmetric functions generate the ring of symmetric functions. That's Newton's result. So the ring of symmetric functions we could write as polynomials in E1, E2, E3, etc. So it's just sums of products of these elementary symmetric functions. So the above, if we make this so the above is a good definition of a map. We make this a ring homomorphism. Now I claim that, well, from the example, it looks plausible that omega not only sends, say, E3 to H3, but it also sends H2 to E2. That is, it's an involution. Now, involution is a fancy word for apply the map twice and you get the identity map. another way to say that, given our definition of omega, is that omega of hk equals ek. Now, since the Schur function s lambda equals the determinant of the matrix whose entries are h lambda I plus j minus I, and s lambda transpose equals the determinant of the matrix whose entries are e lambda I plus j minus I. So we see that the map that takes every elementary symmetric function to a homogeneous function apparently takes s lambda transpose to lambda, or equivalently s lambda to s lambda transpose. Now, since Sn is the determinant of the matrix whose only entry is Hn, so Hn and Sn are the same thing, we have Hn, let's see, omega of Hn equals omega of Sn, which is S to the n transpose, S sub n transpose, which is n1s, and that is just the elementary symmetric function En. So apparently omega maps hk to ek as well as ek to hk. Well, since we're interpreting this to be a ring homomorphism, omega maps e lambda to h lambda to e lambda, s lambda to s lambda transpose. Also, we can use power series to show that omega of p lambda equals -1 to n minus length of lambda, where lambda is a partition of n, p lambda. So the power sum symmetric functions, if you like, are eigenvectors of this map omega. And here lambda is a partition of n. So we see all of our favorite bases here except for the monomial symmetric functions. So it's natural to ask, what is omega of m lambda? Well, I guess we express m lambda in terms of elementary symmetric functions and then just change them all to homogeneous symmetric functions. And there's not really a nicer description than that. So we define a new symmetric function f lambda to be omega of the monomial symmetric function m lambda, whatever that is. That's called the forgotten symmetric function. This is sort of an artificial definition. So it's just whatever omega m lambda turned out to be. It's possible to describe the forgotten symmetric function, the expansion of it, in terms of monomial symmetric function. So it turns out to be -1 to the n minus length of lambda sum over partitions mu of lambda. I'm going to call the coefficients capital A lambda mu and mu. Where A lambda mu equals the number of rearrangements alpha 1 through alpha L of lambda such that every partial sum mu1 up to mu I of mu is also a partial sum alpha 1 up to alpha j of alpha. So for example, let's expand the three forgotten symmetric functions for n equals 3 in terms of the monomial symmetric functions. So we're going to look at the number of rearrangements of the one part partition 3. So there's only one rearrangement, 3. And the sign is -1 to the n, which is 3, minus length of the partition, which is 1. And the number of rearrangements such that every partial sum of mu is also a partial sum of alpha. So if mu is 1, 1, 1, we've got a partial sum of 1, a partial sum of 2, and a partial sum of 3. And they're not all partial sums of 3. If mu equals 2, 1, then we'll have a partial sum of 2, which also doesn't appear in the set of partial sums here, just 3. So I guess M3 is going to be the only monomial symmetric function that appears in the expansion of F3. And then F2 equals -1 to the 3 minus 2, because there's two parts of 2, 1. We won't have M111 appearing because the partial sum 1 is not a partial sum of 2, 1. Our only partial sums here are 2 and 3. And there's two rearrangements of 2, 1. 2, 1 and 1, 2. Our partial sums are 2 and 3 for the first one, and 1 and 3 for the second one. So M111 can't appear because we would need to see partial sums of 1, 2, and 3, and neither rearrangement of 2, 1 gives us that. We're going to have M3. Actually, both of these have 3 as a partial sum. And then M21, well, M21 has partial sums 2 and 3. So only one of these rearrangements contains the partial sums of 2, 1. And F111 is -1 to the 3 minus 3 parts. There's only one rearrangement of 111. It contains M3 as a partial sum. It contains 3 as a partial sum. It contains 2 and 3 as partial sums. And it contains 1, 2, and 3 as partial sums. So these are the expansions. And I guess I can simplify this by writing each minus 1 to a power as plus or minus. So we have f3 equals positive m3, f21 equals negative 2 m3 minus m21, and f111 equals positive m3 plus m21 plus m111. All right, now all of our other symmetric function bases, I should say f lambda, lambda partition of n, is a basis of the homogeneous degree n symmetric functions. Now all of our other bases have corresponding bases of the trace space. So as long as we have an artificial basis of the symmetric functions here, let's define a corresponding artificial basis. I'm going to call this gamma lambda to be, define this to be the corresponding, the trace function corresponding to f lambda. Corresponding by the Frobenius characteristic map. So now we have 6 bases of degree n homogeneous symmetric functions and the trace space of Sn. We have homogeneous symmetric functions that correspond to induced trivial characters, elementary symmetric functions that correspond to induced sign characters, Shear functions correspond to irreducible characters. And then we defined power sum traces corresponding to power sum symmetric functions, which are basically cycle type indicator functions. Monomial traces sort of artificially defined to be whatever corresponds to the monomial symmetric functions. And now we've got forgotten symmetric functions and the forgotten traces. The end.